Good morning, everyone. This is our deep learning project, frequency aware multitask learning for generalizable deepfake detection. And this is our final presentation presented by Nadia and Amal Fouda. Moving to our problem statement, deepfake detector perform incredibly well in lab conditions, over 99% AUC on clean data. But the moment you compress those videos, like what happened on social media, performance collapse. Our baseline IECCE drops from 97% accuracy on clean data down to 74% on heavy compressed video. That's 23% gap is the problem we are trying to solve. So moving to our data set, we used face forensics, which contains 1,000 real and 4,000 fake videos across four manipulation methods: deep fake, face-to-face, face swap, and neural texture, split into train, validation, and testing. We trained on C23, the clean version, and tested on C40, the heavily compressed version, to simulate real-world conditions.
We surveyed five models. Our ECCE stood out. It had the best cross data set generalization, publicly available weights, and clear weaknesses we could build on. And this is made it the ideal baseline to start from. And then For this slide just highlights why RCCE is the best model. Like I mentioned, it has the best cross dataset generalization. The weights were publicly available, and it had weaknesses that we can improve and build upon when moving forward. So let's just take a very quick look on what the architecture looks like. Our ECCE uses an exception encoder to extract spatial features, then a decoder to try and reconstruct the face. The key insight is that fake faces fail to reconstruct accurately. Graph reasoning fuses multi-scale features, guided attention highlights manipulated regions, and final classifier outputs real or fake.
So moving to our proposed improvement, we proposed three addition to our ECC. First, a frequency branch using the FFT, which is fast Fourier transform, to extract GAN fingerprint invisible in spatial domain, fuses through a learned gate. Second, the CBAM attention channel and spatial attention at three encoded stages to focus on manipulation prone regions like eyes and mouth. Third is a multitask head, adding manipulation, type, and segmentation heads during training to force feature learning while keeping only binary classification at an inference. So, moving to our data processing, for processing, we configured the pipeline, extract 32 evenly spaced frames per video, and we detected and cropped faces to 256 by 256 with 81 point landmark, then generated dataset JSON split by manipulation type for training.
Moving on to our proposed and our implemented changes. First, initially, we wanted to add a frequency branch, and the goal of this frequency branch was to use is used to FFT to extract GAN fingerprints invisible in the spatial domain, fused through a learn gate. And we were able to implement it in our first milestone, and we saw a clear improvement. However, the improvement wasn't that great. So we decided to do some training improvements, and these training improvements involved data augmentation, increasing the number of frames from 4 to 8, and higher regularization. And through this, we were able to achieve a higher accuracy, even though it was, as you will see in the results, not that high. It was higher than the cross database generalization. And then we continued from this setup, which was our best performing setup, uh, to um, to implement two other attention-based mechanisms, CBAM and multi-head attention. So in CBAM and multi-head attention, the goal of them was to have three encoder stages and to focus on manipulation-prone regions like the eyes and the mouth. And this was for the CBAM attention. And also, it's important to note that in the CBAM attention, we tried different encoder stages, such as 1 and 2, and then we landed that 3 is the best number to be able to improve our accuracy. And finally, our multitask head, the goal of it was to focus training on richer feature learning while keeping binary classification only at inference.
So moving to our result here our result, the baseline sets to at 97% C23 and 74 C40, a gap of 0.23. Adding a frequency alone barely moved the needle. CBAM alone jumped C40 to 80.48. Combining CBAM with frequency, surprisingly hard C40 performance. But our best run CBAM plus frequency plus multitask had achieved 97% on C23 and 81.6 on C40, and this cutting the generalization gap from 0.23 to 0.154. That is a 33% reduction in the gap. So
يعني this
moving to the learned outcome.
and these are graphs that just show what Amal has just said, and the confusion matrix which highlight all the results. Moving on to the demo of our actual work. So as you can see, this is just the website which contains all the data that you have seen, and then we have the live demo. So first off, we've inserted a video, and this runs our RCCE model, which contains the best fake run, and this video has been generalized as fake, and then we will, and it was actually a fake video, and then we will insert a original video or a real video, um, and then as you will see, it will classify it correctly as real, and this uses our best run, which contains both TBAM, multi-head attention, and frequency, and our learned outcomes.
Our learning outcome, the key takeaways: frequency augmentation pushed the model beyond pixel level detection. CBAM recovered the forgery signals that augmentation alone missed, and all the three components are complementary augmentation diversities. What the model learns, attention, sharpen how it applies that knowledge. Moving to our future work. For future work, we wanted to evaluate an additional benchmark like DFDC and CDF to further test generalization. We also want to explore light backbone like EfficientNet, reduce inference time, and investigate adaptive frequency gating and adjust dynamically paired compression level. Finally, adding temporal modeling across frames could help capture inter-frame inconsistencies that signal frame model like our currently miss. Thank you.
And this is our contribution for the final milestone. And after each milestone, we mention the contributions. Thank you very much.